beautiful properties of the character tables.
I'd like to thank the organizers for inviting me to speak. So I was investigating the representation theory of finite groups, and in particular, I was very interested in seeing what sort of combinatorial sequences you can find inside the character tables of well-behaved groups, finite groups, for example, Wreath products, and that's the one. Those are the ones I'm going to talk about now. So first,
you're going to explain what it is.
I'm going to explain what it is. I'm going to start close to zero, so in case, just to refresh people's memories. All right, so let's just start with some basic representation theory to introduce the cast of characters. So let V be a group. All right. And for our purposes, the order of the group will be finite. Okay. And consider a representation rho from G to GL of V. And this is just going to be a homomorphism of groups, where V is a finite dimensional in our case. So it's a vector space over a field, and we're going to fix the field to be C. Makes everything nice. Okay, and again, assume everything is finite. Okay, great. All right, so whenever I refer to representations, I may refer to rho, comma V, or simply V, when rho is understood. All right. So this is what a representation is. So let me. Okay. And I want to define what an irreducible representation is. So what is a? So to do that, I have to introduce subrepresentation. So a subrepresentation. Here I'll. Of V is a linear subspace. Let me use this. Linear subspace U of V, U inside of V, such that rho of G applied to U stays inside of U. Okay. So any of these matrices or linear endomorphisms that G is mapped to will just send U into itself. This is a subrepresentation. And an irreducible representation. I'll call this an irrep, or irrep pin sometimes, is a representation, V, such that V is non-zero, and V has no proper, non-trivial subrepresentations. Okay. Good. So, let me give you a quick example of a representation. In this case, I'll give you an example of a representation of Sn. So let Sn be the symmetric group. We'll be looking at the symmetric group a lot on n letters. On n letters. Then we can take V to equal Cn, since our space, our field is C. And so this will be the set of all n tuples of complex numbers, and the symmetric group will act on these n tuples of complex numbers simply by permuting the indices. This is a representation. It's just an action that cooperates with the linear structure of the vector space. right, so this is an example. So here, x2, this is the explicit action. And whenever you have it like this, you have this funny so on. You have this sigma inverse acting on these indices just because this is how it works. Okay. And this is a left action. Okay, very good. So now that we know what a representation is, let me say some facts about this. Okay. So the first fact is that, fact one, every finite dimensional representation, V, can be written, can be decomposed as a direct sum of irreducible subrepresentations. Let's call this N. So where the VI are subrepresentations and therefore representations in their own right, and they're irreducible. Okay, for all I. Okay, this is called Maschke's theorem. We won't prove it, though it's easy. Okay, we have another fact. Well, since this is true, we only care about the irreducible ones, okay? Because we can always break it down into its constituent parts. So fact 2 tells us the following thing about the irreducible ones. The number of irreducible representations, in this case, is equal to the number of conjugacy classes in whatever group we're dealing with, G. Okay. And we'll just call this C or CG to highlight the dependence on G. And what I mean by number of irreducible representations, I mean the number of equivalence classes up to isomorphism. What is an isomorphism of representations? It's just an isomorphism of vector spaces that respects the action of G. You can just talk about it that way. Okay, great. So these two facts will be very useful in talking about characters. So let's define characters. So here I'll define this. This is important. So so V is a representation. It's a representation of the finite group G. Then a character. Then character, or the character rather. The character. Chi of the representation V is a map. It's a map from G into the underlying field. And all it is, it's the trace map. So it's the trace of rho of G, where rho is the homomorphism corresponding to the representation. Okay. Since it's a trace map, and rho is a homomorphism, it turns out that it's constant on conjugacy classes. So the proof is just one line. So chi of H, G, H inverse is equal to just the trace of rho of H, rho of G, rho of H inverse. And this is just chi of G, because traces are constant on conjugacy classes. Okay. So this is useful for what we're going to be discussing. One more fact we need. So suppose, fact 3. So if V is a direct sum of two subrepresentations, where V is a representation and the VI's some representations of V. Then the character of V, we'll denote it chi V, is equal to, you can guess, the sum of the characters of the components. Okay? So that means not only that we can can we reduce the problem of understanding representations simply to understanding, boiling it down rather, to the irreducible representations, but if we want to understand the characters of representations, we only need the representations corresponding to the irreducible guys. Very good. What's good about the characters is that they characterize the representation. So if you have two distinct representations, by distinct I mean non-isomorphic, then they'll have necessarily different characters. So in order to understand the full representation theory of a group, of a finite group at least, we only need to look at the values of these maps. And we can encode that very nicely in a matrix. This matrix we call the character table. Okay, so the character table of a group G is the C by C matrix it'll be chi I, let's say, gi I ranges from, sorry, j, I and j range from 1 to C, where chi 1 and so on, chi C are the characters of the irreducible representations. So this will be, I'll call this the irreducible characters. And the GI, so G1, G2, and so on, these are representatives of their conjugacy classes. I say a system of representatives of conjugacy classes, to be more precise. So, and here we've just exploited the fact that that it's constant on conjugacy classes. So this is this little one-line proof, and the fact 2, that there are the same number of conjugacy classes as there are irreducible representations. Okay. Great. All right, so let me give you an example of a character table. Okay, the simplest one. So, example. Am I writing dark enough? Should I press more?
No, that's good.
Okay. All right, so I want to give you the character table, let's say, of S3. It's the first sort of non-trivial one. To do that, I should talk about the conjugacy classes of Sn. This is sort of standard. So to do that, I'll talk about partitions. So maybe I'll call this definition, and then we'll go on to the... So a partition, lambda of n, so let n be some non-negative integer. And this is what we'll use to denote a partition, is a sequence lambda, so lambda 1, lambda 2, and so on. You can take it to be infinite, such that the sum of the lambda I greater than or equal to 1, is equal to n, and it's weakly decreasing. So this is a convention. So lambda 1 is greater than or equal to lambda 2 is greater than or equal to, and so on on and so forth. Because of this finiteness condition, this sequence has to become zero eventually, stabilizes at zero. Okay. And so we'll denote the number of positive terms, we'll call that the length, and denote it by L of lambda. So this is the length of lambda, and this just equals the number of strictly positive terms. Okay, great. Hey, should I continue here, or do you want me to start again? All right, so this is so we need this. Okay, great. And so the conjugacy classes in Sn are determined precisely by, or they're indexed by, partitions. Okay, so this is a standard result. So if you have an element sigma inside of Sn, then sigma can be written as a product of disjoint cycles. Okay? So sigma is equal to, let's say, A1, A2, and so on, B1, B2, and so on. And the lengths of these things, of these cycles, rather, we can call them lambda 1, lambda 2, and we could just have initially ordered them so it went from longest to shortest. And the conjugacy class of sigma are all the permutations in Sn with the exact same partition, lambda 1, lambda 2. So is indexed, is given by cycle type. This is called the cycle type. This is lambda. Lambda 1, lambda 2, and so on. Okay, great. Now, in general, this is sort of unfortunate. Even though we have the same number of irreducible representations as we have in conjugacy classes, for a general group, it doesn't seem to be a map or a natural map other than just the bijection between the two sets to identify an irreducible representation with a conjugacy class. Okay. I don't know of any. I don't think there exists one. But in the case of Sn, we're lucky. There is a sort of natural map from partitions to irreducible representations. Okay. And so we can sort of relate them that way. But of course we needed this intermediate object to establish that map. Okay. Maybe I should draw the diagram. So in general, we can give a partition by a sequence of numbers. We can also draw them. And so we can draw a partition using Young diagrams or Ferrer's diagrams. So let me just introduce this right here before I move on. Or Ferrer's diagrams. And so I'll just give the definition by example. So if we have a partition lambda equals, let's say, 4, 2, 1, then the diagram would be you put 4 boxes in the first row, 2 boxes in the second row below it, 1 box in the third row below that. So this would be 4, 2, 1. Okay, so this would be the diagram corresponding to the partition. I didn't want to spend too much time on this. All right, now I still haven't given you the character table, let's say, of S3, so we'll do that now. So I'll draw that here. Character table of S3. And so the irreducible representations, I'll write them up here. The corresponding partitions, I'll write up here. So let's start this way. This one, and then this one. And then here, I'll put the cycle types, but I'm going to put them backwards, just because I prefer it that way. So, show you why. So this cycle type corresponds to the identity element. And this one to the 3 cycle. And in the usual scheme that I use to talk about irreducible representations of the symmetric group, this one I usually reserve for the trivial representations. This is the one where the homomorphism over there just sends everything to 1, to the identity. And that's why I write it this way. So I'll write it like a table. And this is just going to be trivial. The trivial is all one-dimensional. This one will be the sign permutation. So it assigns the sign of the permutation here. So this is a transposition. This is a product of 2 transpositions. And then this one is the so-called standard representation that happens to have these as the characters. Okay. And in fact, you can get the standard from this permutation representation by modding out or taking orthogonal complement to the vector 1, 1, 1, 1, 1. That's irreducible. And it corresponds in the case of n equals 3 to this one.
But the trace of the identity matrix is linear, general M.
Oh, for this one, it's the subspace orthogonal to
yeah.
1, 1. So it's 1 less dimension. Okay, so there was a story of Gelfand that one time he made a graduate student come up and write the character table of S3. So I made sure as a first year to memorize this, just in case it ever came. Okay. Right. All right. That's the character table. But how to compute them, other than being scared into it by tales of old great mathematicians? So, fortunately for us, there's a way to compute. Let's see how much time. Okay. Try to speed it up. So, a way to compute the characters very explicitly using symmetric functions. Okay. So, what are symmetric functions, or in this case, symmetric polynomials? So here. I'll just give you what you need for this talk. Okay, so consider the following ring. And so these are the polynomials with entries in C that are invariant under the action of Sn. What's the action of Sn? Permutation of the variables. Okay. So an example of one of these would be, just x is equal to x1 squared plus x2 squared, and so on, squared, or x1 times x2 times x3, etc.
The homogeneous?
I'm taking them homogeneous. They don't have to be. So yeah, I don't have to. Okay. So what do I want? I want to give you 2 bases. Just 2 bases. Tons of bases. Okay. So I don't even want to go. There's a veritable zoo of symmetric functions that act as bases for these. And what's good about them is that they're indexed by partitions. So now that we know everything about partitions, this will be easy. So the first basis I want to give you is the power sum basis. This is how we produce them. So first define P0 of x, say that this is just 1, and then say PR of x for r greater than or equal to 1 is just xi to the rth powers as the sum of the rth powers. I equals 1 to n. Greater than or equal to 1. Okay, so in fact, we can show that the PR, including 0, they generate lambda n. Okay, they generate it as a ring. They're not a basis quite yet, but if we define, so let lambda be a partition of n actually, p lambda to be just the product. I'll suppress the x all the way down. These, the collection of these, for all partitions of arbitrary n, form a basis of this space. Okay, very good. So this is the first basis. So p lambda is a basis. And lambda is a partition of some integer n. So is a basis. Lambda n. Very good. So now let me give you another basis. The second basis I'm going to give you is the Shor basis, the Shor function basis. Okay, so what are the Shor functions? Well, I can just give you the definition. So this is S lambda of x is equal to the determinant. It's given in terms of determinants. And over the determinant of essentially the same thing, except no lambda minus j, same as well. Okay, this is a symmetric. Let's see the time. This is a symmetric function. Why is that? Because the numerator and denominator are antisymmetric. The denominator divides the top one. And in the interest of time, I won't tell you why. So this is indeed a polynomial, and in fact, it's a basis. S lambda of x is a basis of big lambda n. Okay, now we have two bases. What do we do with bases? We find their transition matrices. Why else would I give you two bases? And so miracle. The transition matrix, let's say p mu to s lambda, is precisely the character table of the symmetric group. All right, great. So let's just leave it at that. All right, so lambda and mu are partitions of n. So, there are details, so I'll have you fix a homogeneous component, but let's not get into that. So, because of this, we can teach Maple and ourselves to explicitly compute these characters simply by decomposing power sums as sums of Shor functions. So we have,